Hi, my name is Jack, and this is my Week 6 composite body project dealing with deformation maps and deform length. So I like to start with my results just to show what we're working towards in the geometry we're dealing with. This is my defined geometry. I've used it in a couple previous weeks. That bottom shape and that top shape are called a frustrum, and then the middle is just a rectangular rod. This is our deformed composite body, and we end up looking at this length right here is what I determine, is what I calculate by hand. You can see there's a lot of lengths that got determined here, so that's pretty cool that it was able to go through all those lengths very quickly. So I started off with a deformation map. This deformation map you look back at the frustrum, the way I kind of think of it is if these were fixed ends, and if you rotate it 90 degrees, this would be like a beam. And then there's a force acting on kind of this edge right here, pushing it towards this side. So this, you can see that here. This is kind of a higher magnitude in the x2 direction, a lower magnitude in the x1 direction. And then I included just some deformation in the x3 direction, just so that you could see another cool application of this math. I just wanted to make it more difficult, really. So I went through, I then did x to z, which is just the vector field plus 1, and then you sub in the z's. And then the deformation gradient, just the derivative of that for each term in each basis. And that's how I got my vector field that you put at the bottom of the code. I then just went through for each body, and this is the bottom body. This is how I've defined it every week. I just put it in for z this time. The tangent, you can just, you look at your body and you're able to take that down very easily, especially for this body. The map comes from this equation right here, just plugging it in for our geometry for this body. Same thing for fmap, just plugging it into our big matrix with the current geometry. This is what we end up getting. Very similarly for body 2, we go through those same equations just for this geometry, and here are the equations we found. Not too complicated, getting the code wasn't that bad. And body 3, very similar to body 1, just upside down. One of the things that's interesting about this body is that the center is actually here. That's really the most complicated part about this code, is that we're not starting at the base and going up. Every single one has to be translated to get that kind of effect. So this was the figure we saw as our results before with the deformed vector. In MATLAB, you can actually click on the points in the corner and find what their locations are. So first I took my figure and I took those points and I just did the length equation, and I got 8 and 8.15. The return on it was also 8 and 8.15, so I knew those two agreed. And then I did what was shown in the project video, where you take the form length. I just did a regular length equation for the first one, and then the second one I took the deformation vector, used it for this curve geometry, and then did the derivative of that, used the integral of the magnitude of the derivative of that curve over its from 0 to 1, because that's what the parameter u is maximum range at, and you get 8.154. So that confirms that those two are the same. At the end, I just showed my hand calcs for, this was my body f map when I found it by hand, and then I wrote it using latex. This was the curve code, and then this is body 2 and body 3. Alright, and then this is my MATLAB code. Just show it running. Come on, little buddy. And there we go. There is our deformed body. Alright, thank you.